Hi, welcome back. So in this video, I'm going to discuss about one of the most prominent reference models that is used in computer networks, which is the OSI reference model. So before we start the discussion regarding the more reference models or OSI models, what the layers are, first let us talk about why do we need a reference model and what is a reference model. So in simple terms, a reference model is a conceptual layout specifying how communication should take place between devices. Now let me put it in this way. Now, if you are using, let me say a particular Bluetooth technology, doesn't matter where you buy a Bluetooth component, it works the same all over across the entire world, right? In similar way, if you are a manufacturer and if you are manufacturing a particular component, whether it might be a Wi-Fi component or it might be an Ethernet component or something else, you need a particular standard, right? How to define or how the communication should take place. That is actually provided by a reference model. Now I have brought a small example for you guys, like just a blueprint for a particular building. Now, initially, when you want to start to construct a building, you don't just go buy the materials and start constructing. First, you get a model, see how it is, the dimensions and everything. So irrespective if the people change or if anything changes, the model remains the same because that model is a standard for building that particular apartment or whatever it might be. Similarly, a reference model is a kind of layout specifying or standardizing how communication should take place between two devices. Okay. Now, why should we study a reference model? There are two primary benefits why we should go for a reference model concept. The first one is standardization. I just gave you an example of a Bluetooth technology. If you are buying a Bluetooth component or if you are buying something else, it doesn't matter where you buy it from or whom you buy it from, whether it might be Samsung, Redmi, Apple, Windows, Microsoft, doesn't matter. So all those manufacturers have to prepare their components with the same standard. So they work with one another. The second most important benefit is multi-vendor development environment. Now, if you want to buy a switch or a router, just go into Google and go to one of those e-shopping websites like Amazon or Flipkart. You find a lot of different options, right? You might find some from TP-Link, Netgear, Cisco, D-Link. You have different vendors who are trying to sell their products. Doesn't matter which vendor it is always the same. The particular router does the same task or the switch does the same task. So when you standardize the components, when you standardize how each thing should work or what each thing should do, doesn't matter who is producing it or who is manufacturing it, you have a healthy competition so that the price remains the same and new things start coming up. So these are the two primary benefits of a reference model. The first one is standardization. The second one is a multi-vendor development environment. It doesn't become a monopoly. So if you want to buy a router, I can't just simply go to Cisco. Cisco should not be the only one company which produces routers. There must be other people too. So this is how it is being done. And as I told you, there are two primary reference models that are used. First one is the OSI model, and the second one is TCP/IP model. In this video, I'm going to concentrate more on the OSI model concept. What is an OSI model? Who came up with it? All those things are covered in this video. Okay. So first things first. What is an OSI model, and who is responsible for it? You must have come across the term ISO, the International Organization for Standardization. Some people might say International Standards Organization, but this is the more specific way of reading it. International Organization for Standardization. It is an independent, non-governmental, international organization dedicated to worldwide agreement on international standards. It consists of bodies from almost all the countries across the world who come together, who decide what type of standard should be given and so forth. So an ISO standard that covers all aspects of network communication is your OSI model. OSI stands for Open Systems Interconnection. OSI stands for Open Systems Interconnection, or simply put, OSI model, which has been introduced in from 1970s onwards. You might ask me, sir, what do you mean by open system? An open system is one which is actually open to communication, or which has the ability to communicate, send and receive data. Such a system is called as an open system. And in order to connect these open systems together, this reference model has been proposed. Okay. Now, The purpose of this OSI model, in simple, one more thing. So if you read the ISO model in the reverse order, that gets your OSI. So ISO stands for International Organization for Standardization, and OSI stands for Open Systems Interconnection Model. The purpose of OSI model is to show how to facilitate communication between different systems without requiring changes to the logic of the underlying hardware and software. If you remember my earlier videos, I told you that computer networks is a complex system. It consists of both hardware and software which should work in synchronization. It is not a simple system. So in order to tackle this big problem of communicating between devices, programmers or designers came up with the idea of breaking this big problem into manageable subproblems, and we name them as layers, right? So each layer has got some particular task. There comes the question, how many layers should we have? Is there a specific limit, or is there a specific standard on defining how many layers should a reference model have? OSI usually has 7 layers. Where did the 7 come from? How did you reach the conclusion that OSI must have 7 layers? TCP/IP has 4 layers. So how do you decide it should have only 4 layers? So for those things, I wrote this. In 1983, Day and Zimmerman published a paper where they laid down certain principles that were applied to arrive at the 7 layers for which OSI have been developed. So they gave you some rules on deciding, on which would help you to decide how to get or how to decide how many number of layers that your model should have. The first principle is each layer should perform a well-defined function. So a layer should have a specific task. Simply put, that is what a layer should do, a particular specific function. Okay. The second one is a layer should be created where a different abstraction is needed. That means a change, a different way if you want, then only you should create a layer. So you cannot create a layer for similar functionalities. Only a different abstraction is needed, only then a new layer should be created. The third one is the function of each layer should be chosen with an eye towards defining internationally standardized protocols. So if you are defining a layer to do some particular functionality and you develop a protocol or something which would satisfy that functionality, it should be done in such a way that it simply can't be implemented for one set of protocols or one set of technologies only. It should be developed in such a way that it can be standardized, which could be implemented on a global level. So that must be your idea. So the function of each layer should be chosen with an eye towards defining internationally standardized protocols. The next one is the layer boundaries should be chosen to minimize the information flow across the interfaces, which means that when you define the layers, obviously communication happens between vertically, right? Between adjacent layers, the data will be passed on to the bottom layers. You have to define the interfaces in such a way that there must be not too much of information that is flowing across the boundaries. The overhead should be kept to a minimum. You can't expect adding thousands and thousands of bits to send maybe 1 or 2 bits of data. So the interfaces must be clear. The boundaries between the layers should be chosen to minimize the information flow across the interfaces. And finally, the number of layers should be large enough that distinct functions need not be thrown together. And at the same time, it should not be too small enough that the entire architecture becomes unwieldy. So you can't have too many number of layers, and at the same time, you can't have too few number of layers. According to these principles, based on these principles, OSI model have been proposed with 7 layers. The 7 layers are, if you start reading, the topmost layer is your application layer, followed by the presentation layer, followed by the session layer, then comes the transport layer, then comes your network layer, followed by the data link layer, and the final layer is physical layer. Usually, the way how you read these layers defines the approach that you follow. One of it is your bottom-top approach, which starts with the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. The other one is a top-down approach, which starts with the physical application layer, ends with the physical layer. It's based on the textbook that you are referring. Usually, I refer Tenenbaum's book and Faruzan's book and Kurosaw's book. Tenenbaum and Faruzan do the bottom-up approach where they start with the physical layer and then proceed on towards the application layer, whereas Kurosaw's textbook starts with the application layer and ends with the physical layer. Okay, so let us discuss what each layer does briefly, and then we can discuss them a little bit more in detail. Okay, first comes the physical layer, which is the bottom layer of your model. This layer has a single responsibility. It has to convert the bits which it receives from the upper layers into signals for transmission across the media. So whichever media is there, let it be a copper media, let it be an optical fiber, or let it be a wireless media, doesn't matter whichever media it is there. The physical layer's duty is to convert the bits into signals for transmission. So which signal will it use? It is dependent on the media present. If it is a copper media, it has to convert it into an electrical signal. If it is an optical fiber, it has to convert it into an optical light signals or light pulses. Or if it is a wireless media, the bits have to be converted into an electromagnetic waves and then transmitted across. On top of the physical layer, which is your second layer, is called the data link layer. This layer organizes the bits or organizes the data that is passed on from the upper layers into frames. And once the framing is done, it provides error control and also flow control. We will discuss what those are in a few minutes time. The third layer is your network layer. So this network layer is it actually handles how the identification of the end devices across networks, addressing, routing, which is the optimum path from A to B. If you are sending data from A to B, which is the best path to choose while traversing different networks, that is what your network layer does. So it provides addressing, routing of packet between different networks. The next one on top of your network layer is your transport layer. Transport layer does provide the reliable process-to-process delivery, and it also provides error control and flow control. The difference between the network layer and transport layer is network layer will find out the machine to which the data should be transmitted, and transport layer handles the data according to the process on that machine. We will discuss more in a few minutes time. On top of your transport layer is your session layer. So this session layer actually handles session management and synchronization. How to start a session between two machines, and also session management includes whom to talk, who should talk, how much time should they talk, how to clear out a session. All those things are handled by your session layer, how to termination, all those things. And on top of session layer is your presentation layer. So presentation layer, the name itself tells you, it has to present the data to the application. So it handles translation, encryption, and compression of data according to the format or according to the protocol required at the application layer. The final and the top layer, which actually provides an user interface, is your application layer. Application layer is the layer where a user can interact with the network services. Okay, so application layer provides user access to network services and resources. One common thing which I found, which my students keep asking me is, sir, should we remember the layers only in this particular order? The answer is yes, you have to remember the layers in this order only. Generally, there are two common ways which I found of remembering. There is some phrase. The two phrases are, the first phrase is, all people seem to need data processing. This is one. So A stands for application, and P stands for presentation, S stands for session, T stands for transport, N stands for network, D stands for data link, and P stands for physical. So this is the one way of remembering from top-down approach. The other way of remembering, if you want to use a bottom-up approach, this is another phrase. Please do not tell sales people anything. Once again, physical, data link, network, transport, session, presentation, and application. I have to share a funny thing with you. When I was discussing this in my class a long time ago, one of my students said, sir, rather than these two things, I have a better way of remembering. We are from the state of Andhra Pradesh. So he said, sir, Andhra Pradesh state transport not developed properly. That was even more catchy and fun to remember the order of the layers. So Andhra Pradesh, A stands for application, Pradesh, P stands for representation, state, S for session, transport, not N for network, developed, T for data link, P properly, P for physical. So Andhra Pradesh state transport not developed properly. All your 7 layers are there. If you don't want that, you can still use these 2 things. All people seem to need the data processing, or the other way is, please do not tell sales people anything. But the order is important. Doesn't matter which phrase you use to remember the order, but the ordering is very important. If at all you are asked to write down these things, you should be always in a position to write them in the proper order only. Okay, if you see these arrows actually depict the information flow between the layers. So any information, in our earlier videos we discussed about the hierarchy of layers and layered architecture. Similarly, at the sender, the data will be passed on from application to presentation, presentation to session, session to transport, transport to network, network layer to data link layer to physical, where the data gets converted into signals, and the signals are transmitted across the medium. At the receiver side, the physical layer receives the signals, decodes them back into data, and handles the data to the, or handovers the data to the data link layer, which it gets processed and it forwards it to the network layer. And similarly, the data will move on to the upper layers till it reaches the application layer, where it is displayed to the user. This is how usually communication takes place in networks. Okay, let us start discussing each layer in detail. The first one is your physical layer. I told you the physical layer is the lowest layer in the hierarchy, and it defines rules by which bits are passed from one system to another on a physical communication medium. Okay, so it defines the rules, how the bits are passed. What do you mean by the rules? Actually, physical layer is the one where it connects to the physical media. It might be an STP cable or a UTP cable or an optical fiber or a coaxial cable or even let us say wireless medium. So it covers all the mechanical, electrical, functional and procedural aspects for physical communication. What type of coding schemes are used, how the signal should be sent, whether you are using what is the voltage that you are using for an electrical signal, what is the duration of each bit. All those things are covered by your physical layer itself. So the characteristics such as your voltage levels, timing of the voltage changes, physical data rates, maximum transmission distances, the physical connectors. You can see here, this is an RJ45 connector, this is a BNC connector, this is a subscriber tip connector. There are different types of connectors used. All these connectors come under the purview of your physical layer only. So physical connectors and other similar attributes are defined by the physical layer specifications. So in a nutshell, physical layer is the one which actually accepts the data from the upper layers, converts them into signals and transmits them across the media. So that is what your physical layer does. On top of the physical layer is the data link layer. So data link layer attempts to provide reliable communication over the physical layer interface. I told you that physical layer deals with all the interfaces and stuff. It simply converts the data into signals and transmits them, but it does not care for any transmission errors. So it is up to the data link layer to ensure that this physical layer appears error-free to the upper layers. The upper layers like your transport network and other layers should not be bothered about any transmission errors that are happening at the physical layer. So for that purpose, what you do is the data link layer prepares the data or packages the data into frames. So the frame is nothing but it is a unit of data at the data link layer. So it packages the data into frames for transmission across the medium. And once you do that, it now can handle error control by implementing an acknowledgement frame and automatic retransmission scheme. So error control, all these things are actually discussed in detail in our future videos. So error control means that you have to ensure that whichever frame is being sent, that frame is actually being received without any errors at the destination, whether they are received in order or not. And in case if there are any errors that happen during transmission, you have to implement an automatic retransmission. What this means is, if this is a sender, and if a sender has sent a frame to the receiver, and if that particular frame contains errors, automatically lack of an acknowledgement means the sender should retransmit that frame again. Okay, so in this way error control is handled by the data link layer. We will discuss more about the error control in our future videos, how it is being done, how we can use the sequence numbers, timers, acknowledgements, all put together for proper implementation of error control at the data link layer. We will discuss them in our future videos. The next one, or the next functionality of the data link layer, is also to implement flow control. Flow control means that a sender simply can't send the data according to his will or according to his own data rate. It has to send the data in such a way that it is acceptable for the receiver or not. So if a receiver can accept maybe only 5 frames per second, the sender should also send only 5 frames per second. It simply can't send 100 frames or 200 frames per second according to its speed. So how do you do that? That is, though, are the techniques that we implement are put together is called as the flow control. So implements flow control, which prevents a fast sender from drowning a slow receiver and data. So this also should be taken care by your data link layer only. So error control, flow control, and framing. So these are the 3 main functionalities that are handled by your data link layer. Now, data link layer has got 2 sublayers. It is actually divided into 2 sublayers. Namely, one of it is called as LLC, logical link control sublayer, and the other one is called as medium access control or MAC sublayer. Now, LLC, it actually is the one which communicates directly with the network layer because it sits here, and it also handles the error control and flow control. Then what does medium access control do? Or why are we defining a separate sublayer called as MAC? This sublayer is very important in case of broadcast networks, because I told you in case of broadcast networks, all the hosts or the systems are connected to a single channel. And that means a single medium is being shared among multiple machines. Then how do you decide which system or which host should use the medium? How much time it has to use the medium? All those things are actually now handled by the MAC sublayer. So it handles broadcast networks by providing controlled access to the shared medium. So the MAC control or the MAC sublayer plays a crucial role in case of broadcast networks or broadcast channels. So this is regarding your data link layer. Let's move on to the network layer. So I told you earlier that network layer's primary responsibility is to move packets. Of course, I have written here frames here, but it has to move the packets across the network by finding the best path or an optimum path between the source and destination. So if I'm having this diagram, I have taken it from Kuros and Ross textbook. You can see there are a lot of things. Now this one here, which is shown, this is the representation of a router. A router is a network layer device which connects different networks. So a router. Now all these lines coming out of a router are called as its interfaces. Okay. Now if you see in this example, there is an end system H1 here, which is made by a laptop, and this H1 wants to communicate with another system called as H2, which are on 2 different networks. Now how it is being done? Here, the network layer's responsibility is to first identify both these 2 systems. How H1 is identified and how H2 is identified. It defines logical addressing called as IP addressing first to identify the end devices so that they are clearly identified on the across this internet or across the network. The second one is how does a packet from H1 reach H2 through the best path available. So it defines the most optimum path the packet should take from the source to the destination. Okay. How does it do? There is a technique called as a routing. There are many algorithms that are defined. A routing means it is a network-wide task of finding the best path or the optimum path from source to the destination. Some people might get confused with another term called as forwarding, because usually when we talk about network layer, they do talk about forwarding also. Please remember that forwarding refers to the router's task of deciding which outgoing link should the incoming packet be forwarded to. This forwarding decision of deciding which outgoing link is coming from your routing table or from your routing algorithm. So routing refers to the network-wide process from A to B, which is the best path or which is the optimum path. Forwarding is actually done at one particular router. If you take this as an example, here, once a packet reaches this is the incoming line. This router has to decide whether to forward it onto this interface or this interface or this interface. There are 3 interfaces for this router to take a decision. There is an internal routing table which is maintained in the router, which tells if your destination is towards this network, you take this path or this path. That decision is done by the routing. And once it is done, this packet is simply forwarded on to this particular interface. Now I'm keep on talking about interface. Interface is nothing but the link between the router and the physical medium. So this is an interface, this is an interface, this is one interface, this is one interface, and this is one interface. And the IP addresses are actually assigned to these interfaces on a router. Okay. So it defines logical addressing so that any endpoint can be identified. Just now I told you H1 and H2. This is actually achieved by using IP addressing. The IP addressing is of two variants now, IPv4 and IPv6. IPv4 is the old one and IP version 6 is the latest one, IP addressing. It also handles congestion control and quality of service issues in the network. So if a particular network is getting too congested, if there are too many packets, it has crossed across, it has crossed the threshold of the capacity of the network, then the network layer has the ability to change the path, to take an alternative path, just like how you do with a Google Maps. If you open a Google Maps to your destination, it will give you 2 or 3 alternate routes. If you see that one route is purely red in color, then you will automatically select another route. Similarly, it handles the congestion control and quality of service issues in the network. Okay, quality of service is discussed earlier. It is nothing but if you have to satisfy the requirements of a particular flow. If you whatever requirements a traffic flow needs, if you have to satisfy them, then that is called as quality of service. Now it facilitates interconnection between heterogeneous networks. Networks need not all be the same. You might have different types of networks, but still network layer is the one which actually allows you to connect different networks also. We call it as internetworking. In broadcast networks, the network layer is thin or non-existent, simply because just we discussed that in broadcast networks, all of them are connected to the same medium. Then what is the purpose of finding where the particular system is? Because any data that is sent on a shared medium will be received by all the machines. So in such cases, in broadcast networks, the network layer is thin or in terms non-existent. So this is regarding your network layer. I've got another example for you, so that to better understand the concepts that we discussed till now, which includes your physical layer, data link layer, and network layer. So let me just tell you, this diagram is taken out from Faruzan's textbook. Now imagine that A wants to communicate with EF. Okay, so what does system A do? It prepares the data, an application layer, and it forwards the data onto the next at the bottom layers. So here is the network layer. It prepares the data in the form of packets. It forwards the data to the data link layer. The data link layer will create a frame and it will forward it to the physical layer, where the physical layer will treat the data as bits and convert them into signals and forwards it onto the medium below, which is now reached or which is now taken up by the B, or this router is B. So this data is received at B, and B will have its own physical layer. So it will decode the data, or it will decode the signal, convert it back into data, gives it to the data link layer. Here the data link layer will search for any errors, will look for any errors. If there are any errors, it will ask A to retransmit the data. And if there are no errors, it will simply forward this data to the network layer of B. Now at network layer of B, it has to take a decision because B has got 2 interfaces, right? There are 2 options for B. Based on the destination's address of F, B has to take a decision of forwarding this packet on which of these interfaces. Now, according to its routing table, it knows that in order to send to F, it has to forward it to E. So that decision is taken, that information is set up into the packet, and it is forwarded back to the data link layer again. This data link layer will create a new frame. It will hand over it to the physical layer. The physical layer once again will convert it into the signal based on the medium present between these 2 nodes and forward it on. So these signals are transmitted across the medium here till it reaches E. At E, once again, the same process is repeated. The physical layer will convert the signals to data. handovers it to the data link layer. The data link layer will check for any errors, and then it will forward to the network layer. Once again, the network layer will now find that E has a direct link to F, and it will put that information here, and it will forward it onto the next machine. So it will put it here. It will create a packet here, and this packet will be taken up by the data link layer. It will create a frame, and it forwards to the physical layer where the bits are converted to signals and they are transmitted over here. So in this particular scenario, what I want you guys to observe is the data link layer, or in short DLL, is also called as a hop to hop layer, because it takes care of frame delivery at each and every hop. So from A to B is one hop, B to E is another hop, E to F is another hop. At each and every hop, data link layer works such that, or to ensure that whichever transmission errors, if they are, if any, happening at the physical layer, are taken care of. You can see data link layer is working at each and every layer. Network layer is called as an end-to-end layer. End-to-end layer, or sometimes called as source to destination layer, because the network layer duty is to identify the endpoints of A and F. For this purpose, it uses the IP addresses. Okay, IP addresses are called as logical addresses, whereas MAC addresses defined at the data link layer are called as the physical addresses. MAC addresses are called as physical address. Okay, so this is how it is usually done. Now, what is the duty of the transport layer then? We defined three layers: physical, data link, and network. I told you just how these three layers work together for ensuring the data delivery between A to F. Then what does the transport layer do? Transport layer is called as a process to process layer, simply because once the data reaches F, on F you might be having different applications running at the same time. Then how do you decide to which process or to which application should this data be delivered? Imagine that you are watching a YouTube video, playing a game, listening to music, three applications at the same time. And if a packet arrives, how does your system know to which application should this packet be delivered to? There comes the concept of a transport layer. The basic function of this layer is to provide a reliable mechanism for the exchange of data between two processes. Do you understand now? Two processes. Network layer identifies the machines. Transport layer identifies the processes. So it accepts on different computers. It accepts data from above layers, splits it into smaller units if needed, and ensures they are delivered correctly at the other end. So network layer's purview is finding out the machines A and B, but the transport layer's duty is to ensure reliability of data communication between the processes. Imagine that this is your YouTube server and this is your YouTube client. So whichever data is coming from the YouTube server must be delivered to the YouTube client only, such that you can't expect data from one process to be delivered to another process. For this purpose, what we use at the transport layer is something called as ports. We shall discuss about the concept of ports in our later videos. At the network layer, we use the concept of IP addresses to identify the host. Okay, and a transport layer to identify which process should the data be delivered at the destination. We use the concept of ports. Port and an IP address put together is also called as a socket address. Generally, socket is defined as the endpoint of communication. So transport layer accepts the data from the above layers, and if your data does not fit the MTU, it might divide it into smaller pieces, which we call them as segments. And then they are delivered to the destination, then where they are reassembled and passed on to the upper layers. So your transport layer ensures in-order delivery of messages without errors, no packet loss, and no duplication of messages. In other words, it provides the reliability factor. Reliability means you have to ensure that each packet is delivered without errors only once and must be delivered without loss. So all these three are ensured at your transport layer. And based on the type of application you are running, it can either provide a connection-oriented service or a connection-less service. It is up to the application. So which type of service we want. And we discussed about these two services in our earlier videos. So based on the requirement of the application, you can either go for connection-oriented service or a connection-less service. So this is regarding your transport layer, which brings our discussion now to the session layer. On top of the transport layer is your session layer. Session layer allows users on different machines to establish sessions between them. So if there are two machines A and B, and for A and B to establish sessions, the work is actually taken up by your session layer itself. So there are three things. There are the three types of services which session layer provide. The first service is called as the dialogue control. If two people are talking, you imagine that there are two machines, A and B. If there are two machines, A and B, if both are communicating, dialogue control is a service which provides permissions such that only one person can speak at a time. That means it actually controls the communication. Dialogue stands here for communication. So who talks, whose turn it is where it should, whether A should talk first or B should talk first, and after B, who should talk again. All those things are handled by the session layer in the form of dialogue control. The second one is token management. It also ensures that the two hosts does not do the same critical operation at the same time. So it handles token management. If A wants to do something, do some modification or do some particular sending of data, it will ensure that only A does that and B does not disturb in the middle. That is actually taken care by your token management. The last one is called as the synchronization, where you can see in this particular diagram, the black colored ones, they are nothing but checkpoints. Now, if it's a long session, if it's a large session, long transmission, it is of a long duration, it sets up checkpoints on the path in such a way that if at all anything happens to the session, maybe a power failure or a crash of a system, these machines can go back to that checkpoint and resume from that point, need not start from the initial stages. So setting of checkpoints during long transmission to allow them to pick up from that point in case of a crash or a failure, just like how you use your checkpoints in a game. If your lives are lost, you need not start from the scratch. You can go to the older checkpoint and start from that point onwards, right? Similarly, session layer also allows you to set up checkpoints or synchronization points, which the two machines can use to start from that point onwards in case of a power failure or a crash or anything. Okay. And it handles session termination also, session establishment, session management, session termination. All those things are handled by your session layer. On top of your session layer is your presentation layer. The name itself, I told you, the name itself tells you that how it takes care of how the data is presented to the upper layers. So based on the format, based on the protocol, based on the application, how the data should appear to the user. So the presentation layer defines the format in which the data is to be exchanged between the two communicating entities. It deals with the syntax and semantics of the information transmitted. So syntax means it defines the structure or format, meaning how data is ordered according to the protocol's definition. So you have a protocol. So how the data should be ordered according to the definition or the standard of the protocol. Okay. Then what do you mean by semantics? Semantics means it refers to the meaning of the data. It determines what individual field or pieces of information means to the protocol. Okay, within a network protocol, if I am having a particular field, what does that field tell you, or what does that field mean? What is the meaning of that particular field? All those things are taken care of by the semantics. So the presentation layer actually deals with syntax and semantics of the information transmitted. It is responsible for protocol conversion, character conversions, data encryption or decryption, even expanding graphics commands and data compression also. So all these things are handled by your presentation layer, simply because its responsibility is to ensure the data is presented according to the user's application. So this layer ensures that the data is sent in such a way that the receiver will understand the information and will be able to use the data efficiently and effectively. So whichever protocol is being used at the application layer, according to the protocol, your data will be modified or your data will be presented in such a way so that the receiver can understand. That is the reason your presentation layer is also sometimes called as the translation layer or the syntax layer. Okay, so syntax deals with the structure or format of your data, and it is the duty of the presentation layer to do that. So that is the reason we call the presentation layer as the translation layer or syntax layer. Now we have come to the last layer or the topmost layer of your OSI model, called as the application layer. It serves the application layer's primary duty is to provide an user interface. So what do you mean by an user interface? It serves as an interface for users and application processes to access the network services and resources. For a user to interact with the network, maybe to send data, to receive data, to do whatever he wants, your application layer is the one which actually provides these services, or which actually provides the interface through which a user can interact or can start or can initiate communication with the network. It consists of various protocols that are commonly used by applications, including the file transfer, electronic mail, audio video streaming, and multimedia. Simply put, almost all the different types of protocols that we use regularly, all of them fall under the purview of your application layer. Each one of these protocols is designed to give you a particular kind of service, or let me put, to support the applications that you require. So all those things comes under the application layer. Now we defined and we explained the functionalities of each one of the 7 layers. This is the diagram which will tell you how the communication takes place. As I told you, imagine this is your sender A and this is your receiver B, and you have 2 other machines sitting in the middle, 2 routers C and D. So the application layer on A will accept the data and it will start sending the data or passing the data to its bottom layers, where at each layer a header is being added. So presentation layer will add its own header, session layer will add its own header, transport layer will add its own header, network layer its header, data link layer its frame header and a trailer, and passes on to the physical layer, where the physical layer converts it into signals and the signals are transmitted across the medium. Now, if you see here, the host computers require all the layers, the full stack requires all the layers, whereas the routers here only require the bottom 3 layers. Why is that? Because these 2 machines are responsible for moving the data across the subnet. You can see we call this as the subnet boundary, right? These machines are responsible for only moving the data so that the data goes from source to the destination in the best path. It is not bothered about the semantics or syntax, how it should be presented to the application layer. No, only the end machines are equipped with the full stack of it. Now you can see there are something written out here, APDU, PPDU. This means PDU stands for Protocol Data Unit. PDU stands for Protocol Data Unit. And at the application layer, we call it as an application layer's PDU, data that has been created at the application layer. Now data that has been created according to the presentation layers protocol, we call it as a PPDU, presentation layers PDU. At the session layer, we call it as SPDU, session layers PDU. Once it reaches the transport layer, we call it as a TPDU, transport layers protocol data unit. So what do you mean by this? If somebody asks you what is a PDU, you can simply say that PDU is nothing but the data that is prepared according to the protocol of that particular layer. Now, once you can see, sir, why didn't you write NPDU? Because the common name for an NPDU is a packet. For the data link layers, PDU is a frame. And at the physical layer, we only treat the data in form of bits. Sometimes at the transport layer, we also call it as segments. The data at the transport layer is also called as segments. And if you see some dotted lines here, this is called as protocols, right? So protocols govern the communication between adjacent layers or peer layers. So presentation layer on A communicates with presentation layer on B using a presentation protocol. Similarly, network layer on A talks to network layer on C, talks to network layer on D, talks with network layer on B using a network layer protocol, which is IP. Okay, you can see here, internal subnet protocols are there, communication subnet boundary is given, and how does a host send it. You can see this is physical layer host router protocol, the network layers host router protocol. This is how usually a communication takes place in an OSI reference model. So OSI reference model has got 7 layers: application, presentation, session, transport, network, data link, physical. This communication is physical adjacent layers, whereas communication between peer layers is virtual and it is governed by the protocols. Okay, so hopefully you understood the concept of OSI model and the 7 layers well. So thank you very much for watching, and do subscribe and share if possible. Thank you. Take care.